Welcome back to Math 112. We are going to talk about section 7.2. And 7.2, we're going to get into some more identities, more things you need to memorize. I'm going to break this section up into a couple of different presentations because it's going to get really tedious otherwise. So we're going to start with addition and subtraction identities. And these are things that look like this. So what they tell us is that there are different ways to express the cosine of an angle that is, for example, some other angle, a difference, sorry. The cosine of a difference of two angles can be expressed as the cosine of the first angle times the cosine of the second angle plus the sine of the first angle times the sine of the second angle. What this does is it lets us express more of our angles in terms of known values. So let's take a look at an example. Suppose we want to evaluate the sine of 75 degrees and we don't have our calculator. What can we do? Well, or we want an exact answer and not a calculator answer. We know that 75 is equal to 45 plus 30, right? And our identity tells us that the sine of 45 plus 30, which is 75, can be rewritten as the sine of the first angle, so the sine of 45, times the cosine of the second angle, so the cosine of 30. Now with sine, the sine that we always, if we add here, then we add here, and then it's the cosine of 45 times the sine of 30. Okay, now the reason why this is cool is because we know the sine of 45 degrees. The sine of 45 degrees is square root 2 over 2. We know the cosine of 30 degrees, which is square root 3 over 2, plus the cosine of 45 degrees is square root 2 over 2, and the sine of 30 degrees is 1/2. So this is square root of 6 over 2 plus the square root of 2 over 2. And, whoops, sorry, no, that's right. So we've got now the exact value for the sine of 75 degrees. Okay, let's back up to our identities for a second. There are some things that you can key in on. So with cosine, the expanded form is cosine times cosine, and then the opposite of whatever we have inside, time, and then sine times sine. So cosine alpha minus b is equal to the cosine of alpha times the cosine of beta plus, so the opposite sign here, sine of alpha times the sine of beta. With sine, some things to key in on, you have sine, cosine, cosine, sine. And the symbols then are the same. Bottom line is you have to memorize these. There is no choice. I've put some flashcards on the Canvas shell for you to use in helping yourself to memorize these things. Make your own flashcards, write it out, do whatever you need to do in order to commit these to memory. Okay, so here's another one. Let's simplify sine of x plus y minus sine xy. In other words, we want to reduce this to as simple of an expression as possible. Well, let's start with sine x plus y. we know that the sine of x plus y from our identity is equal to, remember sine is sine and then cosine. And then which? Same symbol or opposite symbol? Same for sine, right? And then cosine and sine. That is the first part. Now we're going to subtract from that. Pretty much the same thing, except what's going to be different? Instead of a subtraction or an addition, we're going to have a subtraction. So it's going to be sine x cosine y minus cosine x sine y. All right, distribute my negative sign through, and it turns out these guys cancel. This becomes a positive, and we just end up with 2 cosine x sine y. And that's it. That's how this thing simplifies. All right, the real power comes in when we're doing things like this, like solving this thing. All right, so we know that if we're going to solve an equation like this, we have to isolate the trigonometric expression. Oh, we can't isolate these trigonometric expressions. There's too many of them. So what we need to do is we need to collapse this all down to just one trig expression. Do you recognize it? Well, let's see. I've got a cosine and a cosine and a sine and a sine and a minus in between. That kind of looks like it might be the sum angle for the cosine. Let's look that up. Sure enough, it turns out that this is the same thing as the cosine of x plus 2x. So this left-hand side is the expanded form of this cosine of a sum. So what we have is the cosine of x plus 2x is equal to square root of 2 over 2. Add these together, we get cosine 3x equals square root 2 over 2. Hey, we know what angle has cosine root 2 over 2. In our unit circle, going around there are 2 of them. So 3x can be pi over 4 or 7 pi over 4, which means x is pi over 12 or 7 pi over 12. Pretty neat, huh? Here's the thing, you need to memorize and recognize these sum and difference identities. Okay, this is a special thing we need to be able to do. You do need to read this chapter. There's a lot more in this chapter that I'm putting in this presentation. One of which is the example immediately before this one in the text. Here's what we're doing. So notice we've got a sine 4x and a cosine 4x. Okay, so we've got 2 sinusoidal functions, 2 periodic functions with the same periods, because that's what the 4x tells us. But then they're vertically stretched. And this function, this question indicates that I can write this as a single sine function. Let's take a look at what's going on here. So let's bring up Desmos. And let's just graph 3 times the sine of 4x. Okay. Plus 2 times the cosine of 4x. Okay, look there. So this is indeed a sinusoidal function. So we should be able to figure out its overall period. Its period isn't just 4x because, let me put the two originating functions on. There's my sine, and there's my cosine. So you can see they're shifted from one another. So when I add all this together, I end up with a sum. My function that it represents, that is the sum of these two functions, has a different period than my initial functions. So how the heck do I figure this out? Because we did this earlier. We looked at the graph and everything was nice and nifty and all lined up. This one, not so much. Even if I try to make this to be, have my pi's on there instead of my numbers, it's still not so nice, is it? No, it's not. So what are we going to do? All right. Your textbook has got a really good set of steps to follow to solve this. And what I'm going to do is I'm going to walk you through those. So remember that if we've got an angle inside a right triangle. Ooh, that's really bad. Okay. Give me a second here. That's a little better. It's a little big, but that's okay. So suppose this is our angle 4x. We know that the cosine, and let's just say that we labeled this as M and N and A. We know that the cosine of 4x is going to be the side adjacent over the hypotenuse, so the length of N over A. And we know that the sine of that angle is M over A. So what we're doing is we are going to say that it turns out that we can do this if we let M be 3 and N be 2. Now, where'd those come from? They came from right here. So my sine of 4x, this is M times the sine of 4x. Okay? This guy is N times the cosine of 4x. Now, from our Pythagorean theorem, we know that we can now find this A. And this A is the same as this A. So that's going to be the square root of 3 squared plus 2 squared, or square root 13. Okay? So we have found our A is the square root of 13. Now, how do I find C? Well, because of what we're doing, and because of the sum angle formula, it turns out that C is equal to, actually the cosine of this angle C, because remember this is an angle, is equal to M over A. So C is going to be the inverse cosine of m over a, which is the inverse cosine of 3 over the square root of 13. Now we'll go to our calculator to get this. So we end up with C equals 0.588. So it turns out that I can write 3 times the sine of 4x plus 2 times the cosine of 4x, and that's going to equal square root of 13 times the sine of 4x plus 0.588. Let's just check that. If I did all that right, then when I graph my proposed function on Desmos, it should line right up over the top of my sum. So the square root of 13 times the sine of 4x plus 0.588. Sure enough, it worked. So here are your steps. And again, these are in your textbook. Just be sure and follow these steps, and it will work out. So you've got m times the sine of something times x, and I forget what your textbook uses. B, I think. Bx plus n times the cosine of bx. And you want to rewrite that as a times the sine of bx plus c. You can find a by taking the square root of m squared plus n squared. B is always going to be whatever is inside. B is your period, okay? And then you find C from the inverse cosine of m over a. Okay, those are your steps. Follow those, it will work out every time, and you'll get to a single scenario. And again, this is why we want to do this. This is the same function we were working with before, the one that comes to the square root of 13 times the sine of 4x plus 0.588. But now we want to find all of the, well, the first two positive x's where that equals 1. Take the sine, well, divide by square root 13. So we end up with the sine of this mess equals 1 over the square root of 13. Which means that this mess, this 4x plus 0.588, is going to equal the inverse sine of 1 over root 13. Now, if you plug that into your calculator, you're going to get 0.281. That is not going to give you a positive x. So how do you find another solution? Well, remember that we've got some symmetry going on. We're looking for the sine function. So by symmetry, there is another solution at pi minus 0.281. Make sure you understand this. Look at your unit circle. Make sure this makes sense to you. If it does not, you need to get a hold of me. Okay? There's going to be a third solution when we go all the way back around the circle. So that's going to be at 2 pi plus 0.281. These two will give you positive solutions, and you solve those, it turns out that x is 0.568 or x is 1.49. Okay. That's it for this part of the 7.2 lecture. Be sure and work on memorizing those identities and make sure you know how to apply them, and I will talk to you all soon. Bye for now.